Hello everyone. The goal of this project is to design and implement a reaction time with digital readout. In this project, we will use the Verilog code and the D0 bar to do the project. First of all, we need to generate a 100 Hz clock from the 50 MHz clock on the D0 board, because the D0 board originally will have the 50 MHz clock. So there is in my code, and we first implement the parameter m is equal to 500,000, and then we need to change it to the change it 50 megahertz to 100 megahertz. Here is the code. This part is the code of our changing clocks, and the new clocks will call the clock 2, and we will use this clock 2 in the continue Verilog code. And for the BCD counter in our project, we will implement the BCD counter that counts the 1/100 seconds of seconds, and here is our BCD count. There is the clock and the clear and enable as the input, and then we do the BCD count in this whole module called BCD count, and this code we can find in the book in the section 5.14. And thirdly, I should display the count of the BCD counter using the 7-segment display, and I will need to show at least 2 digits. Here is the module that we use for the 7 segments, and here is the cases that BCD count. We will have this whole module for the BCD counter, and because we need 2 digital. We need at least 2 digits. So here in the pin planner, we I use here digit 0 from 1 to 7, and here digital 1 to 1 to 7. There is 2 totally digitals. And then to truly test the random time, reaction time, there has to be a random delay between pushing the start button and the actual start of the test. So here, for calculate the random counter, we will use this part of code to do the random counter and set the original is or is equal to 1. And this idea is from the book, the picture of section 5.8. We will indicate this part code and reuse it. So here in my code, I call this is another new module called MUX DFF is multiplexer, one multiplexer with 1D flip-flop. So we will use this and call it as the totally 15 stages to get the input and as the output for the next stage. And fifth, draw and label a state diagram of my reaction time, and here is my state drawer. So initially we will add the W, and if we not push the start button, and we will still circle in this W, and once we push the start time, it will go to the delay state, and the computer will count the delay. If the delay is not equal to 0, it will always stay at this state, and if once the delay is equal to 0, it will go to light up the LED light. And at the same time, the computer will start to the BCD counter, and then if we not push the stop button, and it will always stay at this state and always do the BCD counter. And once we push the stop button, and it will go to display the results on the 7 segments, and we can push the reset to make it all the display result equal to 0. And if we don't push the start again, we will always stay at this result. And once we push the start, it will go back to the second delay state that it will go like we talked before. And so here is my all of my Verilog code. So here is the definition of the input, output, rack, and wires. Here this part is to change the clock of hertz of the clock, and here we do the shift of the digit. And then we call the down count module to down count the number by the random number we got before. And in this always block, we will do to test it is the push or the reset. And then we will call the function to do the 7 segments shown in the board. And here is the call function of the multiplexer with 1 D flip-flop. And this module is to do the down counter. And for this module, we will show the result in the D0 board of the 7 segments. And this is the BCD count module that we will do the BCD count if we are in the light up LED state. And for make the coolness of my project, we can do the same thing. The professor showing the class that we can make the 7 segments doing the moving boards in the 7 segments board. And here is the code that I used. It's the same with we saw in the book in the lecture that here is but it's in the different words. I used the test in 1 0 1 2 3. And here is the rest of my code to make it cool. And then we can process and start compiling of this code, but it's not with the coolness code, but we will compile later. It's compiling successfully, and then we not command this part of the code, and we save it and start compile. So it's also compiled successfully. So this is all of my project. Thank you for listening.